Hello friends, this is Mainak, your Civil Bro. So I've been after a long time. Today we're trying to design a sloped roof in Staad Pro. So it will be sloped RCC roof. You can check out the plan and elevation here, and this the bottom part is this is the plan, and then top part we have the elevation here. So we're going to make a sloped RCC roof here. So it will be the slope will be two sides and the angle will be 15 degree. If we just draw a line through the center, the slope of the roof will be in this direction and this direction. So sloped RCC roof having 15-degree angle, and that's it. So this is the elevation here. It's 2.95 below the slab. If you just take it over the beam, then it will be 3.1. So it will not be like this flat image. It will be a sloped roof. So, first of all, we like to create the stat file new, and creating the stat file, always do it in a folder because it generates a lot of other files. So make sure you have the folder in which you want to create the stat file. We always do that. Let's make the folder, and we have always do work in matrix system and click on create. Now the time comes to create the nodes here. So we like to make our nodes in MS Excel because it's easier, and if your file crashes then you at least have the coordinates here. Sometimes due to wrong program the file instead may crash, so you don't have to insert the coordinates once again. So I'll copy this text here in the cat and put it here, and then we'll just start writing the coordinates here. 0 comma 0, and then we have the 1.95 comma 0. This the next coordinate here. Then we have the next coordinate. So 1.95 into 2 could have always 3.9 meter, this one. So you can see only the x coordinate will change here because the z coordinate remains the same, and we can copy all these three. Let's must change the color this two so that this stands out, and then we'll copy these three coordinates below to these column locations, and here we will insert the coordinates here 2.7, 2.7, and then again 2.7. So now I'll open an MS Excel file. That coordinates X, Y, and Z coordinate, and also the serial number. We'll just look it up from the CAD and then paste it here. Y coordinate is the vertical axis instead, so it will be 0. Let's consider 0 at the plinth level. So we'll put the coordinates here. .9 coordinate 0, y will be 0. Let's align it to the center because I like it that way. And then you can copy the same coordinate, only the z coordinate will change. Let's look it up in CAD. It is 2.7. Let's paste 2.7 here. Copy, Ctrl plus C, Ctrl plus V, and then the serial numbers, that is 1, 2. We have to write 2 also before we can drag. So then we can drag. Just drag it. Now we can copy here, Ctrl plus C, click on 1, Ctrl plus V. Okay. Join this using add beam command. So we'll use this as the plinth level here. So now we will use the node cursor. Select. We will go to select, and we will use the node cursor to select the nodes, and we will go 0.3, which is the plinth height from the ground level, and 1.5, which is the foundation depth. That is 1.8 meters for the foundation uh, beam. Minus because it is in negative direction. Now we'll make room for the tie beams. So tie beams, let the footing depth will at least be 500. So we'll put the tie beams little bit above the foundation level. So it can be zero point 0.7. So, but first of all, we have to select all the nodes here. So we'll go to select, select the node cursor, select all the nodes of the foundation, Control plus C, Control plus V, positive y direction. Let's go 0 point. So we'll have a positive direction. So minimum would be 0.5, 0.7. So the amount which we'll select, we should remember that there will be a brickwork between the tie beam and the plinth beam. So 0.7 will go. So now we have to join these nodes. We can join this using add beams or using translation repeat also. So let's add the first pair, first two levels using the add beam command. First of all, select these nodes, right click new view, or yeah, go new view, and then join these nodes using add beam option. So let's display entire structure. The next set will join using translation repeat command. Let's select the know the distance. Here we go to utilities, node tools, node to node distance. The distance is 1.1 meter. So now I'll remove the distance, node tools, remove node to node distance, go to front view, shift plus 1. This is a shortcut, and select the go to the node cursor, go to select node cursor, and then select the nodes here for the tie beam, and then go to geometry, use the option of translation repeat, y direction 1.1, link steps, okay. Now we'll join the tie beam here along the layout will be the same as the plinth beam. So now this part of the structure is ready. So now we'll prepare for the next part. And before preparing for the next part, let's assign the supports. So we'll create a fixed support and assign it to the bottom of the columns. So the fixed support denote the monolithic connection between the footing and the column, and it also helps to calculate the moments and the forces which we later use to design the footing. So now from the plinth level to the ground floor slab, we have to know the distance for making the next level. So we'll go back to our CAD file, go to the elevation, and let's check the distance from the plinth level to the top of the beam, which is 3.1 meter. So we need to use this value in the translation repeat. Go back to the Staad file, go to front view, select the plane beam, use go to geometry, translation repeat, y direction, with the value of 3.1, use link steps, click on OK, and we have, you can see if you left click, you can see the height which is displayed. If you don't have this feature, let me know in the comments. I'll tell you how to enable the option of displaying the length when you click on the beam or column. So now we are going to put for the slope proof. The slope proof angle is 15 degrees. So we'll use the formula tan theta is equals to perpendicular by base to calculate the height for the 15 degrees. So half of 2.7 is 1.35. So okay, this unit is in meters. So we'll go with meters. You see 1.350. So the unit is in meters, but the dimension units are in mm in this file. So you can see tan theta is equals to perpendicular by base. We know the base 1350, but we don't know the perpendicular. So we know the value of the tan theta and 15 degree for the 15 degree. So like this we calculate the perpendicular, which is 361.665. So we'll give 360, and if you draw this triangle in the AutoCAD and then you measure the angle of the triangle, you can find the angle is 15 degrees. So we cross verified our calculation like this. Very simple. So we'll insert a midpoint just for the ease of making the geometry, and we'll use this midpoint. We'll use the select cursor, and we'll copy and paste so that we can get the desired geometry for the ridge. Select node cursor, select this, Ctrl plus C, Ctrl plus V in the Y direction. We'll have 0.36, and now we'll use the add beam option to join the beam. So we'll delete this beam. This is not required. Select and delete. So the node, extra node which is created, which will also be deleted along with this. That's what the option is showing. Now we can select this and use translation repeat. First of all, you have to know the distance. It is 1.95. Okay, two steps, 1.95 in the x direction. If you look at the coordinate axis in the bottom left of the screen, x direction, one number of steps 2, step spacing 1.95. Not link steps not required. Click on OK. So we'll delete the horizontal beams. Okay. So we're giving these beams just for reference, but these beams are not required. So don't insert these beams just for visual representation. We are showing this, but these beams are not required. These beams will not be there in this position. Okay. Well, just to show you, these beams are added because this is a common mistake which you do. These beams will not be there. We'll show the detailing later. So let's add the properties. This first property will be added for the columns here. So we can select parallel to Y, assign to selected beams, assign yes, and then we can define the properties for, let's define the property for the tie beam and the lean beam as also the same. The reason with we are doing this two separately, because suppose if the member fails, then we can change the value just for ease of convenience later. We're doing this same process. And now the horizontal roof beams, not the slope roof beams. So the horizontal roof beams will assign a greater value. Minimum depth 350 will assign 350 or 300. 250 to 350 we can do. You can use the front views at different angles to assign this. So you can see this is assigned. Now comes part for the sloped beams. For the sloped beams, we can do 0.25 into 0.25, and we also have to make sure we delete the beam at the center. But if you are doing this, I hope you are not. So let's go 0.25 into 0.25. This will just provide a very minimal size here because large sizes can't be afforded here. We'll use different front views to select all the beams. Use this view to, let's use this view. Yeah, this way we can select the beams. You can see beams are selected, and we'll assign the property first, and later maybe we'll delete the beam which is at this range which is not required. Now delete the beams. Now we'll need the roof. We'll insert the roof as a plate element here because we'll also need to provide the load in the plates, because normal way of providing loads will not work. We'll show you later when we come to the loading part. So 100 mm thickness roof will provide here. So we'll I've defined the plate thickness. Now we have to select go to geometry and go and select add plate option. Okay, add plate option. Now we have to click 4 nodes here very conveniently. Okay, so this is done, and then we'll go assign to view. It will automatically assign the thickness of the plate here. You can see this control plus 2 for this view and control plus 0 to go back to the grid view, and control plus 4 for this rendered view which you have seen in thumbnail. So the modeling is now complete. Now the materials is concrete, but just to double check, you can select concrete and assign to view. Sometimes it might, just to double check, assign to view. Okay, specifications not required in this part. It is required to provide in some advanced uh, designs which you can see in my earlier videos. So first of all, here we'll define the seismic mass as the reference load here. So those who are familiar with my videos, you can know the seismic mass here is a full dead load and a percentage of the live load, as you can, as per the IS 1893 or any other seismic code. Okay, so we'll define the seismic mass later after defining. Seismic definitions. Our building is in Tripura, seismic zone 5 in India. So now I'm going to select 1893 2016. We'll generate here the values. So click on add, and then we'll go by zone. We'll go zone 5, and this building will be SMRF. We'll explain this later along with the materials. So structure type is we'll go with all other buildings. There's also, so there are, I have a in a note, many of you might have that. In that note, I have just separated some part of the code which are the important part of the earthquake code. Why this value 0.36 it comes for the zone 5, and what is the importance factor, and the damping ratio, all these things which are taken from the codes, and also in the videos of the response spectrum also you can find that. But some of you are having difficulty in downloading those material. I saw that in the comments, but please suggest a better way to share it with you, because Google Drive is having some problems and unable to find free way to share these materials with all of you guys. If you can suggest a way, please uh, comment, let me know in the comments how we can share the materials. So okay, so we'll come back to that later. Make sure you comment. So this is actually the note which is prepared for ETABS here. Let me show from this also. uh, I think, yeah, we'll have the, RC, buildings with special moment resisting frames, SMRF here, and the response duration factor is 5, which is taken in the stat file, and also for all other buildings the importance factor is 1, and the zone factor for, zone 5 is 0.36, which you can see in this video. So you're using the basic things in this video, and this note is actually for the response spectrum. uh, you know Response spectrum analysis typically in zone 5 we should do, but this is a smaller building and we want an economical design. We're not doing, but technically you should do a response spectrum analysis, but we are going with simple design here. Okay, now let's create the load cases. So Staad wants us, Staad works only when you insert the seismic loads first. So seismic loads in horizontal direction will insert. The vertical also, as per the IS code, we should do in seismic zone 4 and 5, but we're not doing here because to be on the more on the economical side here. So SLX and SLZ you should add here for the horizontal, and if you're considering vertical, you should add SLP, and you should go the loading type as seismic P. Okay, so doing SLX, SLZ, and then you add the dead load and then the live load. So we'll add the seismic load in X direction. So seismic loads act horizontally, so X direction and the Z direction will add the seismic loads. Then the dead load, first of all we'll add the self weight, then we'll add the member load here. So the member load is the wall load which will act. There's 3.1 meter length, you can see, which will minus the beam depth, which will be 0.35. So there will be brickwork. The load of the brickwork on the beam will calculate here. So 2.75 into 19, the unit weight of bricks into the thickness of the wall, that is 0.25 for the 10-inch walls. So we got 13. So let's put minus 13 because it's acting from top to bottom. The direction of the load is from top to bottom, so that's why as per the coordinate system of Staad we are using minus negative symbol, and similarly we can do for the tie beams as well. But let me just show you something first. For the slope proof, as per IS 875 part 1 table number 1, you have several types of tiles and other things which you can insert on the slope proof. So we'll take a floor finish load of 0.2 here, just for the slope proof here. So you might be tempted to add the load like we normally do in the case of flat roof, that is uh, add it like this. Let me show you. What you do normally do is floor loads, and let us 0.2 minus 0.2. So this is not the right way, just showing you why. Okay, just for showing, I'm telling you. So the minimum range here you can see, if we just select the node cursor, select this is 3.1. Y range will see, obviously this is the height, and this is 3.9. So 3.1 to 3.9 we can put it here, minimum 3.1, maximum 3. So yeah, this is not generated. Let's see if this, oh, it inserted it wrong actually, and this would be 3.9. Okay, so that's why it's not showing. So let's ignore this, delete this, and insert into plate, because that's a better way anyway for the slope proof. Okay, but let's assign the load for the walls on the plain beam first. Okay, now we'll add the load for the tie beam. So the length here is, we'll deduct the 0.25 for the beam, 1.1 minus 0.25 for the plain beam, so it's 0.85. So 0.85 into 19 into 0.25, which is the load which will be acting on the tie beam. This is 4.0325. So let's go 4 minus 4 for the tie beams. We'll assign the loads here, and then the load for the slope roof will assign as a plate load. Negative direction minus 0.2. Dead load, add plate load minus 0.2. The it will gy will be the best one. Oh, sorry. Okay, we'll edit it. Click on edit gy, modify, close. So select the plates, assign. Dead load is now completed. For the live load, we'll add using the stat command file. Okay. So live load you can find in 875 IS 875 part 2, and for the slope roof the live load is given in IS 875 part 2, table number 2. So first of all, let's go to the stat command file, utilities, and then the stat command file, and then we'll open the PDF for the 875 part 2, table number 2. So you can see in table number 2, for access not provided for slopes greater than 10 degrees, so it's 0.75 kilonewton per meter square less 0.02 kilonewton per meter square for every degree increase in slope. So it will be 0.75 minus 5 into 0.2. So let's calculate that in Excel. 0.65. Let's insert the value in the stat command file directly. Just copy this, paste it here, 0.65. Control plus S. Now I'll create the seismic mass using the mass generator. So actually the live load is uh, 50% if it is more than 3, and 25% if it is less than 3, as per the 875 IS 875 part 1 table number 10. You can see here. So in our case live load is 0.65, which will be 25%. So we'll fix this. We'll just factor will be 0.25. So seismic weight is very important in designing building for the earthquake load. So if you don't have this version of stat, you can watch out my earlier videos where we can find the seismic mass manually. So let's add the load combinations here. We can also use RCDC also, but in this video we'll just go with, do it in Staad only because it's a very small building. So this is a mistake which we normally do, just showing you without adding the analysis command. If you do, then it will result in error. So we'll close this, and we'll use the analysis commands, analysis design, analysis commands, add, close, run analysis. Yes, no errors, done. And then we'll go to design, select on concrete, and we'll select the parameters here. So we need FC, compressive strength of concrete, and the compressive yield strength of steel. So just click on OK and then define the parameters here. FC will be, I will use M20 concrete, so 20 Newton per mm square or 20 to 10 to the power 3 kilonewton per meter square, 500 into 10 to the power 3 kilonewton per meter square, Fe 500 steel. So let's select all these values and assign to view because concrete and the steel are in the whole building. So we'll use commands here, two commands we'll use, design beam and design columns. Okay, just, oh, the design beam was missed. Click on add. Okay, so in design columns is easy and design beams, you have to select all the beams here. You can note there is no center beam, it is only the plate which is showing. Okay, so we're good. Assigned and yes. Now we can run the analysis once again just to check our design. So let's run the analysis here. No errors. So if you double click, you the concrete design will show the columns are coming. I know it should, all columns should come. You know, four number of 16 bars because the similar structure, and the roof beams 310 means 2 with 216 it should be fine. Okay, if you just calculate by the area, and for overall for the beams 216 at the top, 216 at the bottom should be fine as per the design here 310. Okay, so this we get more or less an idea of the design in Staad itself. For larger structures we use RCDC because you need to do grouping and all, but here not much grouping needs to be done. And you can see we have designed this slope roof. Okay, so these practical problems which structural engineers face, try to share with all of you guys, uh, to and also to learn more from you through your comments also most of the times. So this is an example of a slope roof detailing. You should be able to do the detailing like this. The top will bend, but the bottom will have to, you'll have to give a development length here like this. Okay, so you have to, while making the drawing in CAD, and this is the joint here you can see of the beam and the horizontal beam and the slope beam. The joint will be like this. Okay, so that's all for today's video.